This session is the second half of Mastering the Math for our AP Environmental Science students. My name is Renee McCormick. I'm the Executive Director of Science Programs for the National Math and Science Initiative, and I'm really glad you're here. So let's dive in. I know I used scientific notation as a tool throughout the first half of this particular lesson, but we're going to get a little bit finer detail down onto how we are going to work with scientific notation and why it's useful to us. So I'm going to go through this fairly quickly. Feel free to pause, back me up, and this Texas twang is not going away, but even though I am from Texas, I do talk fairly fast. So we deal with scientific notation primarily because in science we deal with really large numbers like the speed of light or with really small numbers like the radius of a blood cell. So we want to be able to not have to write a gazillion zeros down. It's really a shorthand way for us to deal with really large and really small numbers. A matter of convenience, shall we say. So if we want to do something as simple as express this number right here, this 0.00234 in scientific notation, we have to understand that scientific notation comes in a format of a digit, a decimal, and however many more digits behind it. It depends on how accurately you're making measurements. Could be just 2, could be 3 or 4 different digits, etc. But whatever that is, it's multiplied by 10 to an exponent, to a power, if you prefer. So we have to figure out what that power is when we're given a number like 0.00234. So I'm going to move that decimal until it is behind a non-zero digit. So that means I'm going to write this as 2.34, and then how many times did I move it, and which way did I move it? Well, I moved it to the right, and when we move to the right, we have a negative sign on that exponent, and I moved it 1, 2, 3 places. So that is that number expressed in scientific notation. So all of this is just giving you a recap of what I just demonstrated. So just be sure that you're very clear that when we have negative exponents, we have small numbers. And when we have positive exponents, we have large numbers. This you learned in school first. This we held out on you for another couple of years. So I realize that you're a little resistant to the negative exponents, but you probably are very comfortable with the positive exponents. And it's okay. Just a little more practice and you'll be good with both. You won't have these prejudices anymore. All right, so what does this really mean mathematically, though? Well, for us, since we're going to be doing a lot of dimensional analysis in the free response portion of the AP Environmental Science exam, it means that you're going to be able to go faster with your math than dealing with a whole bunch of zeros and probably even making a goof here and there with all those zeros. So what it really means when we say times 10 to the minus 3 is that we've got 1,000 in the denominator, whether you want to do it, think of it as 10 times 10 times 10, or 10 to the third, or 1,000. When we get rid of the denominator, then this becomes 1 over 1,000 right here, and so that's why we end up with the negative on that exponent. Essentially, in plain English, it means the number's small. Well, how small exactly? You learned first, when you learned decimals in the first place back in probably about 5th, 6th grade, somewhere in upper elementary, that it just meant the number was really, really small. So it's going to be in the thousandths if it's got an exponent of 10 to the minus 3. It's going to be the thousands if it's got an exponent of 10 to the positive 3. And the difference between thousandths and thousands is 10 to the 6, which is a million. So the large number is a million times larger than the small number. And that's what this is asking you to do, to make that comparison. The difference in those two exponents, minus 3 to 3, is 10 to the 6, which is a 1 with 6 zeros behind it, which you know as a million. And one day you hope to put a dollar sign in front of that, don't you? All right, so why do we do this again? It's not that the 2.34 is the most important part of the number, it's the order of magnitude. Oh, now that might be a new phrase for you. The order of magnitude. So when I talk about a million, it's on the order of magnitude of 6. So if we're talking 1,000, the order of magnitude is 3. If we're talking 1,000th, the order of magnitude is to the minus 3. And so when I do lab, for instance, with a room full of high school students, I never care that they get the exact measurement or answer when whatever they're determining. Like say they're determining a molar mass of an unknown compound. I never care that they get that exact molar mass, I care that they get on the same order of magnitude. Does everyone agree to the first decimal place? Or do they agree to the second decimal place, which is even better? That's 10 times better, 10 times more accurate. So you kind of have to think differently about numbers in this course than you may have ever thought about them before. So there are some nuances when you are adding and subtracting. It's a little bit like a trip back to, again, elementary school. You're going to have to line up the decimal places, and I personally think that the easiest way to do this is to go with the larger exponent. So if you want to add and subtract numbers written in scientific notation, you first have to make sure that both numbers have the same exponent on the times 10 to the part. This is my opinion. You can have a different opinion. I think it's easiest to convert one number to the greater exponent. So if you've got a string of numbers, scan them, whichever one has the greatest exponent, convert the other ones to that. It's going to make in my mind, it makes an easier number to deal with. So if I'm going to add something with 10 to the third and 10 to the fourth, I'm going to convert this one to 10 to the fourth. Well, to do that, I have to move that decimal one more place over here. So it becomes 0.52 times 10 to the fourth plus 3.6 times 10 to the fourth. But you may, because you're going to be doing scratch paper all the time in this course because you don't have a calculator, then I like it vertically. I like it in a stacked format when I'm actually going to add things together, especially if it's more than just two numbers. So understood 0 there, put it there if it makes you happy. 2 plus 0 is 2, 5 plus 6 is 11, carry your 1, 0 plus 3 is 3, but add that 1 makes it 4.12, and you simply bring that exponent down. Subtraction works the exact same way. So, what about multiplication and division? Actually, it's easier. So here you're going to multiply the coefficients, and then you just add the exponents on the power of 10. So if I have 4 times 2, that's lovingly known as 8, times 10 to the, what is a negative 2 plus 10? It would be the 8th. So that's just a long way of doing what we just did. So when you multiply, you add exponents. Go ahead, guess what you do when you divide. Go ahead, guess. Yep, you subtract them. Got to do the opposite operation for the opposite operation. So 4 divided by 2 is 2, and now it's times 10 to the, and we're going to subtract minus 2 minus 10, which translates into 2 times 10 to the minus 12. All right, so sample problem 4. Calculate the potential reduction in petroleum consumption in gallons. All right, we had this discussion on the last recording, but just in case you missed it, you need to write all over your free response problems. The more you write on them, the less rereading you have to do. So what am I calculating? Reduction in, that's a preposition, so you also have to respect the prepositions because they're your friend. It's focusing you on what to calculate. Calculate the potential reduction in petroleum consumption. So petroleum consumption is what we're after in, another preposition, same preposition, but another one thrown into this sentence, gallons of gas per year. So gallon per year is what I'm after. The word per is your friend. It tells you whatever's coming next is in the denominator. And that could be achieved in the U.S. by introducing electric vehicles under the following assumptions. The mileage rate for the average car is 25 miles per gallon. The average car is driven 10,000 miles per year. The United States has 150 million cars, and 10, see it's mean sometimes, we don't start sentences with numbers if you're following anything that even resembles 7th grade grammar. So we have to spell out the word 10, but you got to be on the lookout for spelled out words. So 10% of the U.S. cars could be replaced with electric cars. Well, when you get 10%, you're just going to lop a zero off of 150 million cars. So 150 times 10 to the 6th in scientific notation becomes 1.50 times 10 to the 8th, because I had to move this decimal twice. So I have to move it, and I have to move it back 2 more spots when I put it back to the 150. So that's why it's to the 8th. And now, if I'm going to take 10% of that, that just means take one of those off. So 10% is going to be 1.5 times 10 to the 7th. All right, so start with easy simplifications like that, and then translate the numbers into scientific notation. So again, Just saying again that 10% of the 150 million cars is simply 1.5 times 10 to the 7th. So once you get that done, you can go on with your dimensional analysis. So I'm going to start with that, 1.5 times 10 to the 7th cars. Well, I'd like to multiply by something that's got car in the denominator to get rid of car, because ultimately what I'm calculating over here is gallons per year. Now, we talked on the last recording about you may prefer to start at the equal sign and work back to the left. It's your call. You can do this either way you want to do it. But what I do know is I've got 10,000 miles per year per car. Singular car, but per year. So car and year go here, and I've got 1 times 10 to the 1, 2, 3, 4 zeros, so that's the 4th miles. That's what 10,000 looks like in scientific notation. So I've got rid of my cars. I've got year where I want it. I don't want to get rid of that, but I do want to get rid of miles. So what can we do about miles? We already did the 10,000 miles per year, right? 25 miles per gallon of gasoline. Oh, I need gallon on the top, and I need mile on the bottom. So 25 miles per gallon, the 25 goes with mile, and there's understood 1 per 1 gallon. So now, what else have I got going on here? That's it. That's all I need. My miles will be gone, and I'll have gallons per year. So the technique you just watched me do, you notice I circle my units, and I do only my units first, because there is absolutely no reason for me to waste a single brain cell on the math if the units are not going to deliver the units of my answer. Alright, so what does this equal? Well, 1.5 times 1 times 1 is 1.5. But 10 to the 7th times 10 to the 4th is 10 to the 11th. And that's going to be gallons. And that's going to be divided by 25. Plain and simple. Alright, so now you got to think about what's easy for you. I've still got to take 25 and divide it into 1.5. So this is where I like to do things maybe a little differently. I like to make it a bigger number. So I'm going to make it 150, because I know that 25, I think money, I'm thinking like $1.50, and that 25 is a quarter, and $1.50 is 6 quarters. So don't think less of me because I think in money. But I want to make that 150. So I'm going to rewrite this 1.5 times 10 to the 11th as 150 times 10 to the 9th. So I took 100 off of that 10 to the 11 to multiply 1.5 by 100 to get 150. So again, I know that 150 divided by 25 is 6. So 6 times 10 to the 9th is my answer. Back that up, listen to it again, sleep once, listen to it again, sleep twice, listen to it again. You need to get good at this skill. And you will only get good at it with practice. I'm hoping that you had this before, that you had this in middle school, you had this in a chemistry class maybe, or a physical science class, and that this is not all brand new news to you. But if it is, I'm your new best friend. You can just listen to the sound of my voice over and over again and watch what I do until you get it right. And it'd be nice if you turn the sound off and see if you can do it without me guiding you through it. Alright, so that is your scientific notation primer, shall we say, on to things that have a unique purpose in the AP Environmental Science course. We're going to talk about populations of all sorts of things, not just people. I know right now you're very people-focused, all teenagers are, as you should be. But there's all kinds of populations. There's populations of ducks and geese and dragonflies and hummingbirds, which are one of my personal favorites. And my very personal favorite organism is a bat. Populations of bat. Matter of fact, the largest population of bats, the largest colony, I guess is what they really call them, of bats in this continent is in Austin, Texas, under the Congress Street Bridge. Just delightful collection of bats. Now, demographics, you've probably heard of demographics, but demography is this, because ographies are studies, is the study of the characteristics of human populations. So we are going to talk about all kinds of things that undergo population growth rate, but human populations are a big part of this course too. So we talk about the growth rate, the density, the distribution, and any other vital statistic we can come up with. And the In demography, population growth is used informally for the more specific term population growth rate, PGR, and is often used to refer specifically to the growth of a human population of anywhere in the world. So the most common way for us to express this is as a percentage, not as a rate. Well, first we have to calculate the change in a population, because that's what, populations do. They grow and they decline, and so they don't stay static very often. If the birth rate, if people are having more babies than there are old people dying, then our population increases. If it goes the other way around, like when there's a catastrophic plague or flu or something that is killing people off, if more people die than babies are born, then our population starts to decline. It's very common sense. Don't resist the common sense aspect of this course. All right, so we have fancy words for stuff. The crude birth rate. The crude birth rate, CBR, is the total number of births per year per 1,000 people. We know if we'd have done it per 100 people, then we wouldn't have to mess with this percent business, but we didn't. We did it per 1,000 people. And so the crude death rate, go ahead, guess what that is. Go ahead, guess. Yep, that's the number of deaths per 1,000 people. So we have a formula below, shown down here below, where we simply divide by 10 to report the PGR, the population growth rate, as a percentage. And again, we wouldn't need to do this if we expressed them in per 100 instead of per 1,000. So that's the whole point of the dividing by 10, is because we did it in per 1,000 instead of per 100. So if I want a percentage, it means per cent. Cent means 100. How many cents are in a dollar? How many years are in a century? Get it? So it's simply the birth rate minus the death rate divided by 10. All right, we're going to work a problem with that here in a bit. Now, we also have yet another interesting thing with populations, and that's called the rule of 70. And the rule of 70 is this big, long, hairy derivation, meaning lots of math steps to get there, but we're going to simplify it. It is very simply a way to calculate the time required for the population to double. And it's based on population growth rate, so that's why we had to talk about that first, when that growth rate is expressed as a percentage. So that's why we had to get that little calculation, because the rule of 70 uses it. So resist the urge to express the growth rate as a decimal value. You need to leave it as a percentage. So if it's 25%, you're not going to say 0.25, you're just going to toss 25 into that denominator. All right, so the rule of 70 is mathematically expressed as the time for doubling is 70 divided by the population growth rate, but just leave it as a percentage. So how long would it take for a city with an annual population growth rate of 5% to double its population? Well, that would be simply 70 divided by 5, which is 14. Do it longhand if you have to. I'm giving you a minute to process that. This is an easier calculation. How long would it take for the same city to double if the growth rate were 7%? Well, you've got to expect it would take less years if you're making more babies, because that's what the growth rate's about. You've got more babies being born than people dying off. So 70 divided by 7% is 10 years. The math that you're going to see on the AP Environmental Science exam is math like this. It's not going to be uber difficult. They know you don't have a calculator. Okay, this is like the wordiest word problem ever, but it's a good practice for you to start marking them up and getting the important pieces of information kind of marked. You don't want to sit on the AP exam and read this 6 times. So every time you do part A, part B, part C, you'd rather have it marked up so that your eye goes straight to the data. So the fictional country Industria is tracking its population. In 1855, the first year that vital statistics were reported for the country, the population was 1.6 million, with a crude birth rate, CBR, of 43 per 1,000. At that time, the population of Industria was growing quite slowly because it had a high death rate of 41 per 1,000. So in 1875, 20 years later than 1855, keep this in perspective, in 1875, the population began to grow very rapidly as the birth rate remained at the 1855 level. The birth rate remained at the 1855 level, which was what? 43. So I want to link those two pieces of information together. while the crude death rate dropped dramatically, new information, to 20 per 1,000 from 41 per 1,000. So something happened. Got less infections, better health care, maybe new drugs, new antibiotics, antiseptic techniques were coming around about that time period, etc. So population growth continued to increase in the small country into the late 1800s, even though the birth rates began to decline slowly. So in 1895, the crude birth rate had dropped to 37, the crude death rate had to 12 per 1,000, and a complete census was also conducted and revealed that the population of Industria had grown to 2.5 million. By 1950, the population growth gradually began to decline as the death rate remained at its 1895 level. Okay, so its 1895 level was a crude death rate of 12 per 1,000, while the birth rate continued to decline to 22 per 1,000. In 1977, vital statistics revealed that the death rate was 10 per 1,000, and the population had slowed even more to an annual rate of 0.4%. By 1990, Industria had reduced its birth rate to that of its now constant low death rate, and the population transition was complete. Good grief, Gertrude. This is a lot of information to process. When you come across a whole big clump of stuff like this, you might want to just start here and just scan all the data to find the pieces that you need to answer that question. So give it a quick read, come back and scan. It's just two different techniques, and you've got to practice your techniques and figure out which one's going to work best for you and keep you calm. All right, so what do they want me to do? They want me to calculate the annual growth rate of Industria in 1950. So focus on the in 1950 part. All right, where is that data? I'm scanning by 1950, and I just need growth rate. Growth began with decline as the death rate remained 18. The birth rate continued to be 22 per 1,000. All right, so we had 22 versus 12. 12, 22. So that the PGR, population growth rate, as a percentage is equal to the crude birth rate minus the crude death rate, and you can't mess that up, right? You're born before you die. They come in order. It's not tricky. Divided by 10. So what was the crude birth rate? They tried to trick me because they gave it to me in the problem backwards. The birth rate was 22. Subtract from that the death rate, which was up here at 12, and that is divided by 10. So what is 22 minus 12? Expect easy math. We had this discussion before, and I'm going to continue to have this discussion with you. I was a test writer for the AP Chemistry exam several years back, and I was instructed as a test writer to let the problem lead the student, but also to put in numbers that were easy to work with. So you got to expect easy math. So 22 minus 12 is a whopping 10, and 10 over 10 is 1, and so that's equal to 1%. So the PGR is equal to 1%. So then they ask me a different item, which is to calculate the birth rate in Industria in 1977. So if you go back and you read again, in 1977, the crude death rate was 10, because right there, it was 10, and the PGR was 0.4. So I'm solving for a different variable this time. So what they want me to do is solve for CBR. So when I look at this, PGR, population growth rate, is equal to the crude birth rate minus the crude death rate divided by 10. So the first thing I'm going to do is put in that 4%. So therefore, and you can use that little triangle of dots like you use in math class for therefore as well, 0.4% is equal to CBR, which is what I'm seeking, right? That's what I'm looking for. And minus 10, because I had that piece of data, and that's divided by 10 because that 10 is in the formula. All right, so now what? Cross multiply. Cross multiply and solve for this variable. So if you cross multiply 10 times 0.4, don't you get 4? Think about it. So 4 is equal to what I seek, the crude birth rate, minus 10. So what's my next algebraic step? Add 10 to both sides. So therefore 14 equals the crude birth rate. And I am finished. You cannot forget everything every algebra teacher or math teacher has tried to teach you for the last decade or more. All right, so now on part C, they say assume that the population of Industria continues to maintain the population growth rate recorded for the country in 1895. I go back and find that data. Determine the year in which the expected size of the population would have quadrupled. Well, first, I don't think they gave me the PGR. 1855, first year, went to crude birth rate, crude death rate, but I don't see a growth rate in here. It just says it continued to increase, but it doesn't tell me what that was. So I need to figure that out first. So let's get that first. So the PGR for 1895 is equal to that crude birth rate minus the crude death rate over 10. I'm just using that same formula over and over again. So what was the birth rate? 37 for 1895. Yeah, right there. 37 minus the death rate of 12, and that's divided by 10. So that is 37 minus 12, a nice round number of 25, divided by 10, and that's going to be equal to 2.5%. Then I need to use the rule of 70 to determine the number of years it takes for the population to double. So the time for doubling, and where did I get this rule of 70? Right here. So right there. The time for doubling is equal to 70 divided by the PGR. That's why I needed the PGR. So time to double is equal to 70 divided by that 2.5% that I just calculated. And now, what's that going to be? Well, you're going to have to do a little bit of math here. So 25 into 700. Go back to elementary school with me. If I'm going to move that decimal to be able to divide, so now it's 700. So what's that going to be? Isn't that going to be, well, 25 goes into 100 4 times, and isn't 4 times 7 28? So it's 28 years. So you can think about it that way. Think about this as quarters. I would need 4 quarters to have 100, and I have 7 times 100, so that's 4 times 7, or 28 years. We've not answered the question yet. Let's read it again. Determine in which year the expected size of the population will have not doubled, but rather quadrupled. Isn't that a double doubling? Think about it. Yes, it is. So, therefore, 56 years, 28 twice, 56 years to double the population. Yippee skippy. All right. You'll like this next part. It's probably the easiest part so far. Per capita. That's something you've heard. You probably have actually run into this before in like your social studies classes. Per capita is simply a Latin term that translates into by head. And so basically it's meaning the average per person. Per capita can even take the place of saying per person in any number of statistical observances or statements or quotes. So in most cases the term is used in relation to economic data or reporting, but we can also use it in most any other occurrence that involves a population description of any sort. So between 1950 and 2000, global meat production increased from, preposition, 52 billion kilograms to, another preposition, 240 billion kilograms. So those two numbers are linked. And during this period, the global human population increased from 2.6 billion to 6 billion. Good grief. Calculate the per capita meat production in 1950 and in 2000. Okay, so for 1950, that's going to be 52 times 10 to the 9. 1,000, a billion. When we talk about kilograms, etc., then we get into the fact that a kilo is a power of 3, so 10 to the 3rd, so it's because it's 1,000, and then a million is 10 to the 6th, and a billion is 10 to the 9th. So 52 billion kilograms is 52 times 10 to the 9th kilograms. And that was per 2.6 billion. I feel canceling coming out in my future. Makes me happy. So now, what do we have here? Because again, we don't have calculators, so you're going to have to think about this. So doesn't 52 look a lot? I mean, 26, 52, do you get a relationship there of half? So you might want to think about it this way. And make this 26. And if you do that, then this is 10 to the 8th. And so that simplifies to 2. And then what do we do about these exponents over here? That's a 9. So I'm going to subtract 9 minus 8, which gives a nice, delightful 2 times 10 to the 1, lovingly known as 20 kilograms per capita. So you can either go per person, like that, or you can say 20 kilograms per capita. And if you're writing or typing a paper, that's a whole lot easier to do than try to get a stacked fraction in there in typeset. Same song, second verse. Let's do that again for 2000s. What do we have going on there? 2.6 billion? No, that's not right. 240 billion kilograms. 240 times, and a billion is 10 to the 9th kilograms, divided by 6 billion people. That was a little bit kinder, because the 10 to the 9s are going to cancel. So that cancels, and 6 goes into 240 40 times. 40 is known as 40 kilograms per capita. Then they want us to calculate the global change, or the global per capita meat production during this 50-year period, and express your answer as a percentage. Well, 20 kilograms per person to 40 kilograms per person, I don't need a calculation. That's just a simple doubling, so that's a 100% increase. So no calculations necessary here. It was a 100% increase. It doubled, therefore a 100% increase. So you need to be on the lookout for problems that have like doublings and halvings and things that are in fourths and tenths. There's no reason to make the numbers mean. We're not trying to test your math ability. We're trying to test your environmental science ability, but all sciences have numbers involved. We do measure things. That is kind of our thing. All right, so now let's see if you can put all those newly acquired set of problem-solving skills to work. This is a very long word problem intro. When you see something this big, you better grab some writing utensils, note the plural, and start circling, marking, starring, trying to sort through all these numbers so you don't have to reread this paragraph over and over and over again. Do not be afraid to write on your paper. So when West Fremont is a community consisting of 3,000 homes, a small coal-burning power plant currently supplies electricity for the town. The capacity of the power plant is 12 megawatts. Mega means a million. And the average household consumes 8,000 kilowatt hours of electrical energy per year. So that's going to be per year, that little factor right there. The price paid to the electric utility by the West Fremont residents for the energy is a dime per kilowatt hour. The town leaders are considering a plan called the West Fremont Wind Project to generate their own electricity using 10, how many? 10 wind turbines that would be located on the wooded ridges, which is a fabulous place to put wind turbines, surrounding the town. So each one of these wind turbines would have a capacity of 1.2 megawatts, and each would cost the town $3 million to purchase. Each. These eaches are important. Each turbine costs $3 million each to purchase and finance and operate for 25 years. Okay, that's not that bad a price, actually. All right, so assuming that the existing power plant can operate at full capacity for 8,000 hours a year. Okay, that was not given to us up front. So 8,000 hours per year is the best place to start when they've introduced brand new information that was not given to us previously. Question is, how many kilowatt hours of electricity per year? So kilowatt hours of electricity can be produced by the plant in a year. So if they can produce 8,000 hours per year, and they also told us that was 12 million megawatts or 12 million watts then, and it was kilowatts? No, I'm pulling the wrong number here, aren't I? Oh, no, I'm not. So if it's 12 million megawatts, then what does that mean in kilowatts? That means 12 times 10 to the 3 kilowatts. See, if I don't get my units right, I'm not going to get the right answer. So I caught myself on that one. So now, is that going to work out? Yeah, I got 8,000 hours per year that they operate, 12,000 kilowatts. So what am I going to come out with? Kilowatt hours per year, which is exactly what I want. So what is 8 times 12? That's 96. Times 10 to the, so this is 8 times 10 to the third. That's why I did 8 times 12. And so that means 10 to the third plus 10 to the third, which is 10 to the sixth. And what are the units left standing? Kilowatt hour per year, which is exactly what I want. So you can leave it like this, or if you prefer, 9.6 times 10 to the 7 kilowatt hours per year is another way to do it, or you could just write out all those zeros. It's your call. But either way, we're halfway there. Well, okay, maybe a third of the way there. Now what? At the current rate of electricity per household, how many kilowatt hours of energy does the community consume per year? All right, well, how many homes were there? 3,000. Let's start there. 3,000 homes. And they consume, the average household consumes 8,000 kilowatt hours each year. Now, what is the unit that I am looking for? Kilowatt hour in 1 year. Kilowatt hour, year, per home. Okay, so the home's going to drop out basically. I think we're home free. Pun intended. 24 million kilowatt hours per year. Also known as 2.4 times 10 to the 7 kilowatt hours per year, whichever way you prefer. Now, so far that wasn't that bad. See, all that reading, and so far parts A and B were not too nasty. Let's see what they're going to do to us on C. Assuming that the electrical energy of the needs of the community do not change during the 25-year lifetime of the wind turbines. Yeah, right. What would be the cost to the community of the electricity supplied by the West Fremont Wind Project over 25 years? And express your answer in dollars per kilowatt hour. Okay, well, what did we just figure out? We just figured out how many kilowatts it takes per year. So let's start there. 2.7, that's not 2. It's 2.4 times 10 to the 7 kilowatt hours per year. Now what can we do with that? Well, there's 25 years. Okay, so let's figure that out first. So now I can get kilowatt hours at least out of this. And then I can take a cost, total cost, and divide it by kilowatt hours, and I'll be home free. So 2.4 times 25. So 25, 2.4, 4 25s is 100, 2 25s is 50. That would be 600, except for that annoying decimal point, which makes it 60. So 60 times 10 to the 7, also known as 6.0 times 10 to the 8th, if I need it that way, kilowatts. Okay, so what was the total cost? Well, go back and reread that last piece of the problem again, where they said it was $3 million to purchase and finance these for 25 years and operate them as well. And how many were they buying? 10. So 10 times 3 million is also known as 30 million. So therefore, 30 times 10 to the 6 in dollars divided by 60 times 10 to the 7. Now, which way do I want to do this? Let's go, I want these the same. So I'm going to go with changing the numerator to be 7. So that makes that 3.0 times 10 to the 7. Did I do that correctly? Yes, I did. So now my 10 to the 7s cancel out, and I have 3 over 60. So 60 goes into, got to think about my division principles here. 60 goes into 300. Isn't it 5 times? But there's a 0 there, so I have to get all the way over here to 300. So it's a nickel. So the total cost then is $0.05, because isn't that how they asked me to do it? Dollars in kilowatt hour, even though it looks silly. It'd be better to say a nickel per kilowatt hour. A little bit of a mess, but we got there. All right, so recap. What did we do? You're going to do a lot of these cost things, and they often will come at the end of the problem. Trust me, I've read a bunch of them. So you want to just keep the cost part for last, because the cost part is what you probably already understand best in your own brain if you've ever managed your own money at all. So we just needed to know what was the total amount of kilowatts that would be used over the 25 years, and then divide it by the total amount of money that was spent for the 10 turbines over the 25 years. So then it becomes a pretty simple calculation. You're just going to have to get good at doing them without a calculator. All right, so moving on, let's look at the next sample problem. Would it help if I said the final sample problem? Would that make you feel better? And frankly, I think this one's easier than the other one because we don't have as much to wade through here in the beginning. The Cobb family of Fremont, looking at ways to decrease their home water and energy usage, as are your very own parents. Their current electric hot water heater raises the temperature of the water to 140 degrees Fahrenheit, which requires 0.2 kilowatt hours per gallon at a cost of a dime a kilowatt hour. So each person in the family of 4, so 4 people, showers once a day, 1 shower per day, for an average of 10 minutes per shower. 10 minutes per shower. The shower has a flow rate of 5 gallons per minute. 5 gallons per minute. I'm feeling a dimensional analysis fest coming on. Calculate the total amount of water that the family uses per year for taking showers. Well, what did we just say? We just said 4 people. Now I need to get rid of people. They take 1 shower per person per day. So I got rid of people. Did it say for a year? Yeah, per year. So I've got 365 days per year. So that gets me halfway there on my units in the proper place. And then what else do I have? Oh, total amount of water. They gave me a rate of flow, didn't they? 5 gallons per minute. That doesn't cancel anything out. Just added more trouble into my problem. What do I have to get rid of? The per year is in the right spot, so I'm going to circle that, so I'll quit trying to get rid of that. 5 gallons per minute, and then how many gallons per shower? Oh, how many minutes per shower would be even better? 10 minutes per shower. So I got shower out of my life. I'm getting closer. Got minutes out of my life. And I got gallons per year. Does that make sense for total amount of water per year? Yes, it does. It's going to be a whole bunch of gallons. Okay, so now I just need to work this out quickly. And you got to figure out which way you want to go with these numbers. I got 4 times 1 times 365 times 5 times 10. Well, 4 times 5 is 20 times 10 is 200. So I can simplify this and say 365 times 200. knowing that 0, 0 come off first. And now it's just 2 times 365. So 2 times 3 is 6 and 1 makes 7. 730? No, 73,000. 73,000 gallons. Sounds terrible, doesn't it? Per year. Hey, but we look good and we smell good. Both of which are important. So 73,000 gallons, I should say, per year. Calculate the annual cost, assuming that 2.5 gallons per minute of the water used from the hot water heater is hot from the hot water heater. In other words, you do not get in the shower and use only the cold knob. You do not get in the shower and use only the hot knob. So what they're saying is, since 2.5 is exactly half of 5, that the water was a blend of half hot, half cold. So already, I'm only going to heat half of the gallons per year. So what's half of 73,000? Now, you can work it out and put it all into dimensional analysis if you want, but a little common sense can go a long way in getting you started. Expect easy math. Be on the lookout for simple relationships. Okay, 5 gallons per minute, 2.5 gallons per minute. Hey, that's a half. So I can cut this little sucker in half. So that's 36,500. Do the math longhand if you must. Gallons a year that are going to be heated. Well, good Lord, now I've forgotten what the cost was. $0.10 a kilowatt hour. So $0.10 per kilowatt hour have canceled out nothing. So what else do I need to know? The cost was how much? 0.2 kilowatt hours per gallon. Okay, so now let's see if we can get out of a little trouble. Gallon, kilowatt hour, dollar per year. Hey, I'm home free. Okay, so what is that going to be? That's going to simplify to 36,500 times a dime times 0.2 over a year. And what would this whole mess of the units be? A dollar sign. All right, so can you do that? So if you multiply 36500 by 0.1, you just lop off a 0. So that's going to be 3650. So I'm just multiplying by 0.1, just takes one of those zeros off. And now multiply by 0.2. Or I could have just moved a decimal, perhaps. Nope, I was going to have to multiply by 0.2. All right, so 0, and then 2 times 0 is 10, carry my 1. What am I saying? 0, and 2 times 0 is 0. 2 times 5 is 10, carry my 1. 2 times 6 is 12, plus 1 is 13. 2 times 3 is 6, plus 1 is 7. Now let's clean up those decimal places. And that would be 2 decimal places for that 0.2. So I come out with $730 per year. And again, box your answers. On to the final part. The family is considering replacing their current hot water heater with a new energy-efficient hot water heater that costs $1,000 and uses half the energy that their current hot water heater uses. So how many days will it take for the new hot water heater to recover the $1,000 initial cost, initial investment? Well, you just figured out that it was going to cost them $730 a year, right? So that's $730 for every 365 days. Expect easy math. Isn't 365 twice 730? Scratch it out on paper if you need to, but it is. So therefore, it's $2 a day is what the cost of the old one is. Using their old water heater, that's how much they're spending on heating the water for their hot showers. All right, now the new one they just told you is half as much. Okay, so therefore new half as much is going to be what? Not a trick question. Yes, $1 per day. So if it costs $1,000, won't it take 1,000 days? Yes. Common sense prevails. So therefore, the water heater will pay for itself. That doesn't look like pays, does it? Pays for itself in 1,000 days. Is that sufficient? Is that how they asked it? How many days? Yes, that works. Thank goodness they didn't ask years, because that's going to be another calculation, because there's 365 days in a year. So it's going to be a little bit under 3 years, but at least luckily they didn't ask us that. But on a multiple choice question, that may be the kind of thinking that you have to have. All right, I do appreciate your time. I know this was a bit of torture. I hope you have found at least some of this useful. But let me say this. I have a philosophy about learning, and it is that every student is capable of learning whatever they need to learn. It simply comes down to repetition. There is no shame in listening to some of these recordings again and again and again. You take a test, you do poorly, the word problems were your Achilles heel, and so you listen to this again. You might pick up one more trick from just a repetition of listening to it that would help you be a better problem solver. So I'll quit torturing you for now. Until next time, have a great rest of your day.